In the last session, we discussed the concept of the moles and calculation of empirical and molecular formulas, as well as working out the concentration in parts per million. Today's topic is about the percentage yield. So, what is a percentage yield? Percentage yield, how it can be calculated? It's the actual yield or actual amount or practical value divided by theoretical value into 100. Practically, because we are carrying out the experiment, so this value, most of the questions, this value is given. And theoretical yield, what we have to do, or amount of product, we have to first find that, and actual value divided by theoretical into 100, this will give us a percentage yield. So example, if we have 25 grams of iron 3 oxide that reacted and produced 10 grams of iron, and the equation is given. So iron is a product here, so practically how much we are getting? From 25 grams of iron oxide we are getting 10 grams of iron. That's a practical value or actual value. What is the percentage yield? So as the equation is there, we'll take the ratio of the mass, or we can take the ratio of the moles. First convert the mass into moles. So 25 grams of iron oxide is there. Moles equal mass in gram over molar mass. So 25 divided by molar mass of iron 3 oxide. So that is 159.6. 25 divided by 159.6. That will give us 0.1566 mole. So these are the moles of iron oxide. Then we'll take the ratio for iron oxide and iron. From the equation, the mole ratio is 1 is to 2. So if we have 0.1566 iron oxide, then it will be x cross multiply. So when we multiply them, it will come out as 0.313 moles of iron. And after getting the moles of iron, multiply by its molar mass of iron. So 0.313 multiplied by molar mass, so we'll get 17.48 grams of iron. So this is the theoretical value. Theoretically we should get 17.48, but only practically we are getting only 10. And when we work out the percentage yield, the practical value or actual value, which is 10, divided by theoretical value into 100, so this will give us 57.2% yield. And why we are not getting the 100% yield? What could be the reason for not getting the 100% yield? The percentage yield is a process. Basically, percentage yield in a processes can lower through incomplete reaction. So maybe the reaction might not be complete. Like we have 25 grams of iron oxide. So there is a possibility that all 25 gram of iron oxide does not decompose or does not react with carbon monoxide to form this iron. So that is one possibility. There might be a side reaction. What is the meaning that there might be a side reaction? It means maybe iron oxide, iron 3 oxide might react with another substance in the atmosphere, or maybe the iron which is formed, that may react with another substance. So there are side reactions. Loss during a transferring, so that based on the experimental technique. Example, we are saying we have 25 gram of iron 3 oxide, but when we transfer this 25 gram, so maybe 2 gram is lost. So if that 2 gram is lost or 3 gram is lost during the transfer, so we'll not get the same 100% yield, it will be lower. Then loss during purification stages. Sometimes we purify a reactant or product. So during purification, normally it's like for solutions. So when we are carrying out purification, some of the reaction mixture might be lost, which result in lower yield. So these are the possible reasons why we have a lower yield for iron 3 for iron, as we have 25 grams of iron 3 oxide. Is it clear? Discussion and the reasons why a percentage yield might not be 100%, or it will be why it will be less than 100%. So you have to keep these reasons. Then percentage atom economy. What is the percentage atom economy? How it can be calculated? The mass of the useful product or the desired product divided by total mass of reactant or product. Not only reactant, it can be or product into 100. That is known as the atom economy. So, for example, we have this reaction. What is the percentage atom economy for the following reaction where iron is the desired product? So we want to produce iron, and the equation is given that iron 3 oxide reacted with carbon monoxide to form 2 iron and 3 molecules of carbon dioxide. So how to get the atom economy, percentage atom economy, mass of desired product. So what is our desired product? Iron, because we want to extract the iron or we want to produce iron. This is the redox reaction in which we remove reduce ore of the iron. So iron is our desired product as they mentioned. So what is the mass of a desired product? So when you have to check the equation. So mass of desired product, 2 moles are there. 1 mole of iron is 55.8. So 2 moles will be multiplied by 2. So 2 multiplied by 55.8, that's a total mass of a desired product. Divided by total mass of reactant or product. It's up to you which one you want to. It's the same thing. So how to work out total mass? So you have to take total mass of this all. So when we work out the total mass, iron is 55.8, and how many iron are there? 2, plus oxygen 16, and how many are there? 3, plus carbon is 12, how many are there? 3, plus oxygen is 16, and how many are there? 3, and then into 100. So the percentage atom economy for this reaction will come out as 45.8%. So for percentage atom economy, we don't need any experimental data or theoretical data. What we have to do, we just have to use the equation and check the mass from the equation of a desired product divided by total mass of the reactant or product into 100. Is it clear? The percentage atom economy. Then what is the purpose of this percentage atom economy? The main purpose that sustainable chemistry requires chemists to design a process with high atom economy. Like example, you may have two different process to prepare a same product. Example, if we are preparing ethanol. So how we can prepare ethanol? One is by fermentation. So C6H12O6 will decompose into two molecules of ethanol, C2H5OH plus CO2. And the second one is by addition reaction of ethene with steam. So ethene is there C2H5, C2H4, sorry, because it's ethene plus H2O gives C2H5OH. That's ethanol. So when you check, as you can see, when we have only one product, the percentage atom economy will be 100% because mass of a desired product and mass of, total mass of the reactant will be same. So when you divide the same number, it will be 1, and 1 multiplied by 100, that will also give 100. So this will have 100%. This will have a percentage atom economy equal to 100%. But for this one, the percentage atom economy, the first reaction, that will be less than 100%. So which one is a useful process? Because if it's equal to 100%, it means we don't have any waste product or we don't have undesirable products in the reaction. But as you can see, for this reaction, we don't need carbon dioxide, but the reaction produces carbon dioxide. That is not the desirable product. So it will have a lower atom economy. So basically the reaction where there's only one product, then where all atoms are used making the desired product, then it will have 100% atom economy. And if a process does have a side reaction waste product, the economics of the process can improve by selling the byproduct for other uses. Like, how we can check whether this process is sustainable or whether we can do it for a long run. So the undesirable products are there, so these undesirable product, what we can do, we can use them for another process and utilize that. Is it clear why the percentage atom economy, like comparison is there? So you don't need any data for atom economy or percentage atom economy, you only need the equation. Then making a salt, when we are preparing a salt, so basically the reactions of acid are used to prepare the salt. The definition of a salt: when hydrogen of the acid is replaced by the metal, that's a salt is formed. As we know, like example, we have sodium chloride NaCl, but how this NaCl is formed, actually it is from HCl. So when this hydrogen of the acid is replaced by any metal, as in this example it is replaced by sodium, so the product which is formed is known as the salt. And the most common strong acids, as basically acid and bases are used to prepare these salts, or reactions of acids can be used to prepare the salt. So most common strong acids are hydrochloric acid, sulfuric acid, and nitric acids. So if you want to prepare chloride salt, we'll use hydrochloric acid, sulfate salt, sulfuric acid, and nitrate salt, nitric acid. The common reactions for acid or neutralization reaction, acid base react, because when acid react with base, it will give salt and water. So if HCl react with NaOH, it will form NaCl plus H2O. HNO3 react with magnesium hydroxide, it will give magnesium nitrate and water. H2SO4 react with sodium hydroxide, sodium sulfate and water. HCl plus calcium oxide, calcium chloride plus water. So if it is a hydrochloric acid, it will result in a formation of chloride salt. If it is a sulfuric acid, it will form sulfate salt. If it is hydrochloric acid, it will form chloride salt. And when acid react with metal, it will give salt and hydrogen. So we'll see bubbles phase. And neutralization reaction from salt. Bases neutralizes acid, and the common bases are metal oxide, metal hydroxide, and ammonia. An alkali, a soluble base is called an alkali. So all the alkalis are bases, but all bases are not alkalis. And when acid react with carbonate, it result in a formation of a salt, water, and carbon dioxide. So again, we'll see bubbles, and then the salt depending on the acid we use. If it's a sulfuric acid, sulfate salt; hydrochloric acid, chloride salt. Is it clear the reactions of acid to prepare the salt? So salts basically are prepared by reactions of acid. Then how we can prepare insoluble salts? That normally is by ionic precipitation. And the practical steps. So example, preparing a soluble salt and then later insoluble salt. And these are the methods, because you should be able to write in your own words that how a certain experiment is done. So if you are preparing a soluble salt, first soluble salt. So for example, if you are using insoluble base, metal, or solid carbonate. So what we will do first, we'll add a solid carbonate to acid. So like example, a container is there which is filled with acid. So using a spatula, we can add salt to this. Then we add till what point we'll add until no more reaction occur, no more solid dissolve. In case of acid react with metal, like if we are using a metal or metal carbonate, we can see the bubbles. But in case if we are using a metal oxide, we don't see bubbles. So how we can identify? We can identify until no more react. So until unreacted is there, so we know that we have enough acid, we have enough metal oxide or metal or carbonate, and this will turn into a salt solution. Then how we remove this insoluble or unreacted? We can filter it off. So when we filter off, now we are left with salt solution. So when we are left with salt solution, then it's up to you. There are two ways to extract the salt from the solution. One is by crystallization, another one is by evaporation. So you can carry out any one of them after get removing the unreacted metal oxide or metal carbonate or metal. So we can use crystallization or we can use evaporation. Using the soluble basis. So when we are using a soluble basis, in that case, we have to carry out a titration because acids and alkalis are colorless, so it will be difficult to identify the end point when all the acid reacted with a base. So as it is difficult, so first what we do, we'll take a conical flask. After taking the conical flask, then you can use a measuring cylinder or a pipette and transfer that acid or an alkali into a conical flask. Measuring cylinder, there are advantages and disadvantages. Like the advantage of using a measuring cylinder, it will be quick, fast, but disadvantage, it is not accurate. So instead of that, we can use a pipette. The advantage, it will be fast, quickly. The advantage, it will be accurate, but disadvantage, it will take time to transfer. So we have acid here. We add that acid, then we'll add, because acid, we need an indicator which show a color change when acid react with an alkali, and we fill the burette with the base, and we'll open the tap, and time to time we will swirl the mixture so that acid completely mixed with the base. And when we add the base from the burette, once all of the acid reacted, what will happen, indicator will show a color change. Once the indicator show a color change, we'll stop and we'll know the volume of acid used, and we'll use the reading on the this burette to identify the volume of alkali used. And we can repeat the same procedure without acid and alkali to obtain the salt from this solution. The reason why we are not obtaining a salt directly from the mixture which is having indicator, because the indicators are colored like they will show a color change, so that will make a solution colored. So if you try to extract or obtain the salt from this solution, then it won't be accurate, as the crystals will be colored. So if we are using a soluble base, an indicator can be used to show the when the acid reacted with an alkali, and to produce a salt solution using a titration method. Then repeat the reaction without indicator and read the by using a same volume and obtain the salt from this mixture. But normally, using solid base metal carbonate, we should ensure that all acid reacted and the product is neutralized, and in case the percentage yield of crystals will be less than 100%. Why it will be less than 100%? Because when you are carrying out the filtration, so some of the solution will left on the filter paper. Even some of the solution will remain there in a flask or a container. So as some of the solution is still there on the flask or container, so then it won't be accurate. So percentage yield of a crystals will be less than 100% because some salts stays in the solution, and there will also be losses on transfer from one container to another. Is it clear how we can prepare the soluble salts? By using metal carbonate and metal oxide, as well as soluble base, from soluble base metal hydroxide. Then to prepare insoluble salts, we use ionic precipitation. We mix two solutions and a solid is formed, and that solid is known as precipitate. Example, if we mix lead nitrate solution, aqueous lead nitrate with sodium chloride, this will form lead chloride plus sodium nitrate. And when we check the solubility, most all nitrates are soluble, most chlorides are soluble except silver, mercury, and lead. Most sulfates are also soluble except barium, calcium, and lead. And most carbonates are insoluble except potassium, potassium, sodium, and ammonium. So in this case, we'll take equal concentration and equal volume of the two solution and mix them together in the ratio of their volume. Like example, as you can see, lead nitrate and sodium chloride, the mole ratio is 1 is to 2. So when I'm taking the equal concentration, then if I'm taking 10 cm cube of lead nitrate, I should take, for a complete reaction, I should take 20 cm cube of sodium chloride. So when they react with each other, this result in a formation of lead chloride plus sodium nitrate. So to write the ionic equation, we cancel out the common ion in aqueous substances. As you can see, nitrate is common, as well as sodium is common. So what we are left with lead ion plus chloride ion gives lead 2 chloride, or PbCl2. Is it clear? This example, the ionic precipitation to obtain the salt. If the ratio is 1 is to 2, then the volume ratio should be 1 is to 2 as well. If ratio is 1 is to 1, then the volume ratio should also be same. Any doubt in this part? Then if we summarize writing the ionic equation for different reactions, so ionic equation for reaction of acid with metal, carbonate, base, and alkalis. So acid plus metal gives salt and hydrogen. So what we do, we cancel out the common ions. So what are the common ions here? Common ion in aqueous. So we have chloride ion common, so we'll cancel chloride ion. So what we are left with two hydrogen ions. We are left with magnesium atom in a solid state. Then in a magnesium chloride, only magnesium ion we are left with, as chloride is a spectator, plus hydrogen. So solid, liquid, and gas, you will write them as it is their state. And for ions, cancel out the common ion and leave the ions which are left behind. Same thing when acid react with an alkali, give salt and water. So when we cancel out, nitrous acid is there, HNO2. So this is aqueous, and NO2 is there, so that will cancel out. Then when you check the second one, barium is in aqueous, so that's also cancel out. So basically we're left with two hydrogen ion and two hydroxide ion that result in a formation of two water molecule. 2 is common. Equation must be written in a simplest ratio. So that's why 2 to 2, the ratio is 1 is to 1. Then acid react with carbonate, gives salt, water and carbon dioxide. Again we cancel out the common ions. So carbonate ion is aqueous, this chloride ion is aqueous and chloride ion is aqueous. So we cancel out the chloride ion, and what you are left with, hydrogen ion plus carbonate gives water and carbon dioxide. Another example, the equation representing a reaction between copper 2 oxide and dilute sulfuric acid. Write an ionic equation. So first we write solid, liquid and gas as it is. So copper oxide is solid, we write as it is. Sulfuric acid is aqueous, and water is liquid, so we write as it is. Then we cancel out the common ions. Sulfate ions are common in both. So we are left with two hydrogen ion. For ions, we don't write a number in superscript or subscript, but it should be a coefficient. So if for ions, we normally do not write like this. How we write? We represent it's two hydrogen ions are there. Then risk and hazards, how the definition. So the definition of hazard, what is the definition of hazard? Hazard is a substance or a procedure, so it can be a substance or a procedure that can has a potential to do harm. Like something is having a potential to do harm, we call that as a hazard. Like example, we say something is toxic, so it's if you inhale then it will have a potential to harm. Or something is flammable or irritant or corrosive or oxidizing agent or carcinogenic. So or cancer, can cause cancer. So these are refers to hazard. And what is the definition of risk? That is a probability or chance that the harm will result from a use of hazardous substance or a procedure. So this is a probability or chance that harm will result from use of hazardous substance or procedure. Like example, if you are using a toxic chemicals or any procedure which is using say high temperature, so there is a risk involved. So something, if it's having a potential to do harm, we call hazard. And when we are using any hazardous chemical or procedure, then we call that as a risk. Like example, if we are doing fraction distillation of alcohol, so what is the hazard here? Alcohols are flammable, they can catch fire. And what is the, so you will say it's flammable. And what is the risk involved here? That risk is that it can cause fire, as it is a flammable, so it might burn the substance. So risk can be minimized, but hazards are there. And to minimize the risk, what normally is done, like in the lab, we try to minimize the risk. If something is irritant is a hazard. So what we use a dilute acid, alkalis, or we wear goggles. So if something is corrosive, and these are like normally the irritants are dilute acids and alkalis, which for, and how we minimize that risk, we use goggles. Corrosive, normally strong acid and alkalis are corrosive, we wear goggle as well. Flammable, so we do not directly expose to the flame. Something is toxic, we wear gloves or avoid skin contact. And if something is oxidizing, we keep away from the flammable substance, as it can easily oxidize, or substance which can be easily oxidized are not placed closer to the oxidizing agent. So hazardous substances in a low concentration or amount will pose same risk as pure substance. So if a substance is hazardous, even like example, so even if you use low concentration, then or amount will not pose the same risk as a pure substance. So basically what happened, if you are using like acid, strong acid, so in one experiment you use 10 cm cube of strong acid, another experiment you use only 2 cm cube of strong acid. Which one is having a greater risk, a 10 cm cube of strong acid or only 2 cm cube? When you are doing the experiment, which experiment is having a greater risk factor, A or B? If we are using a small quantity, like in experiment A, we are using 10 cm cube of strong acid, but experiment B, we are only using 2 cm cube. Which experiment is having a greater risk involved? So the first one or experiment A is having a greater risk. Why? Because if you are using a larger volume or a greater amount or greater concentration, it will have a greater risk as well. That's why to reduce the risk, we carry out a small scale. And you have to learn the symbols for each, like if something is irritant, then what should be the symbol? Corrosive, flammable, toxic, and oxidizing agent. So you have to learn the symbol for each of these hazards. Then measuring a volume of a gas by using a gas syringe, it can be done. So when as reactants react, they form a product, a gaseous product is there, so we can collect that gas. So a gas syringe can be used for a variety of experiment, and the volume of the gas depends on the pressure and temperature as well. So when recording the volume, it is important that you note down the temperature. Moles of a gas can be calculated by volume, like volume divided by 24, that will give moles. Volume in dm cube divided by 24, that will give us the mole. And what are the potential errors in using a gas syringe? The gas escape before a bung is inserted. Basically, this part is not in contact initially. The bung is not placed from the beginning. It is only placed when you start up the reaction. So first what we did, we add the reaction mixture, example A and B. So we add A with B, and then after adding A with B, then we place a bung here so that the no gas will escape. But the moment when we try to avoid this emission of the gas or the gas release during a process, so we should quickly close this bung so that very small quantity of the gas will escape. And normally what happen, some of the gases like carbon dioxide or sulfur dioxide are soluble in water, so the true amount of a gas is not measured accurately. Like sometimes the gas might dissolve in the mixture, so that gas will not come out from the mixture, so it leads to lower amount of the desired product. Is it clear how we can use a gas syringe to measure the volume of the gas? Then making a solution, how we can prepare a solution, a stock solution. So you have to learn the process. Like example, if I say I have 2 grams of sodium chloride, how I can make a standard solution of sodium chloride? We have the mass here, the solid sodium chloride, but what we need, we want to make an aqueous solution. So what we do, we weigh the required mass of a solute. So like example, in this example, we have 2 grams. Then tip content into a beaker and add. So what we do, like we have 2 grams of sodium chloride, we add to that beaker, and then we add 100 cm cube of distilled water. So we add 100 cm cube of distilled water and dissolve. It can be directly added to this is called a volumetric flask. So you can directly add to volumetric flask, or what can be done. So you have these crystals of sodium chloride and you add 100 cm cube of water and try to dissolve as much as you can. So then the tip content into a beaker and add 100 cm cube of distilled water. Use a glass rod or a stirrer to mix it. Then sometimes the substance does not dissolve in cold. So the beaker and its content can be heated so that it can dissolve faster or greater quantity can dissolve. Then what we do, we transfer this into a volumetric flask. This is a volumetric flask, and pour the solution into 250 cm cube graduated flask or volumetric flask. Then rinse the beaker and the funnel after washing from the, because we how we are adding, we place a funnel here at the top and we add the solution. So maybe some of the solution might left in the container. So to transfer that, we add further more water and then transfer it into a volumetric flask. And then volumetric flask is having one marking, like example here 250 cm cube. So we fill it to 250 cm cube. So now we know the concentration of the solution. How we know the concentration of the solution? We already know the mass and we know the volume, and if mass is divided by volume, so we can have the concentration of this solution. Is it clear how we can prepare a solution for different process? Any doubt in this part? Then regarding the errors, percentage error, uncertainty, that we will discuss tomorrow, and then we'll do questions from related to the topic. Any question related to the class today? Any question or a doubt? So what we did today, already finished 1.1, 1.2, 1.3 we did, and 1.4 is already done, 1.5 is already done, then 1.6 we did in the last session, 1.7 calculating moles and mass, that is the general gas equation is done, atom economy we did today. And then display typical reactions of acid done. The term precipitation reaction is also done. Displacement reaction, that we'll do in the next session, and we'll complete this topic one, which is about formulas, equations, and amount of substance. So I'll end the session and share this recording with you.